Welcome to a webinar, Dynamic Beam Shaping in DED-LBM. My name is Ami Spira and I'm leading the marketing at Civan Lasers and honored to host this webinar. It's my pleasure to introduce today our speaker, Professor Michael Schmidt. Professor Schmidt is the head of the Institute of Photonic Technologies at Friedrich Alexander University at Erlangen, Germany, and managing director of the BLZ Institute. He is internationally recognized for his work on laser material processing, additive manufacturing, and advanced photonics technologies, and has authored numerous publications in this field. Today, Professor Schmidt will share his insights on dynamic beam shaping and its impact on additive manufacturing processes. Professor Schmidt, we are ready to start.
Thank you very much, Ami, and a very warm welcome also from my side. I wanted to say good afternoon, but I'm not sure if it's afternoon for everybody of you. So hello and welcome. It's my pleasure to give you a few, ideas, hints on the topic dynamic beam shaping and DED, of course, laser beam metals. Already beforehand, so I might not go too much into depth into the materialographic section for you, but you can ask later on, or we'll do, let's say, a second webinar on the materialographic things a lot. Why? Because I want to point out the aspect of dynamic beam shaping and why this is also something that is necessary in DED with laser beam. So at first, small introduction. Maybe all of you know, or many of you know already, but then it's like a repetition. How can you do dynamic beam shaping? So I'm talking about ways to shape your wavefront, and you can do this with spatial light modulators. You can use this with deformable mirrors that you might know from astronomy. Acousto-optic deflectors also can be used. Nevertheless, they are more for deflecting beam and not for shaping beams, and have some losses. Well, all of the things you see here have some...
Professor Schmidt, sorry to disturb you, but we don't see your screen. You did not share it.
You don't? Sorry.
No, we don't see the screen if you shared it already.
You should see the screen, right?
We don't see it yet.
I see it on both my computers, so it should be visible for us.
My apologies.
Okay.
Yes. Sorry.
Okay, no problem. And then, of course, phase arrays or coherent beam combining, which I'm going to introduce in the next slides a bit more. And of course, these are phase-only beam shapers, which we should take into account if we think about like more delicate problems like speckle and so on. There's also amplitude-only beam shapers that you can see. And of course, you can use a phase-only beam shaper for shaping the phase of an electromagnetic wave, but you can use it also for shaping the phase and the amplitude if you wish. This is something that goes more in the optics thing. I want to go now a bit more in how does the coherent beam combining work, which is a very promising technology for doing beam shaping. And you can see it here. You have a seed laser. You go into a certain number of phase modulators after that, so you can delay the phase of each. So let's go through here, and now you see where you are. So where the yellow arrows are. We bring the same signal into phase modulators, a number of phase modulators, and they can delay the phase. Then we amplify everything, and then we bring everything together in a beam splitter and project it on the target. So what we finally get is interference pattern that consists out of the delays of the different phase modulators that we have, and we can have a camera feedback to see if we really get what we wanted to have. So this is more or less how the whole thing works to get the desired focus spot. So we have a Civan system here, of course, otherwise maybe I would not give this seminar or webinar. And we use it, and you can see here a little bit more in a 3D configuration how this works. So here you have the different delayed beams, and you can use the programmed delay of the for example, 32 beams to move a spot. You can basically do more, but moving a spot is one thing that helps you to create images in the image plane. And how does it work? And we did some basic experiments here. You can see in the middle here, this is just the interference between two beams. We delay one beam, as you can see, always between 0 and pi. So this means we shift the interference pattern here. If we would interfere 3 beams, this would be something like this. And if we would have an overlay of many beams, we would have a dedicated spot on one position. And what you already also see here, we nevertheless have in an area around here partial beams, let's say residues or higher diffraction orders that we have there. This is due to a limited bandwidth because we do not have an unlimited number of partial beams. So this is more or less how beam shaping works, how Fourier beam combining works. And this is how it's implemented in the Civan system. So in the software, you just program what you want to do. You have the 1 in the middle, and then means you have one focus spot in the middle, or you make a quadratic shape, and you can see then what is the outcome. So this is the quadratic shape. And what you see around here is what you should always take into account. So you have some higher diffraction orders or some residues that are also there and that also have some power. And you can basically program everything you want to, which makes it very easy in a 32 by 32 grid to program different beam shapes. And these can be programmed quite in a high frequency if you wish to. So then, of course, now I was talking about the systems technology, but now why beam shaping at all? And if beam shaping, why then dynamic? So let me give you a small, let's say, more theoretical introduction why that might be or why that is of importance and of a big use that you can have. If you just look on the left side and you see, okay, you would shape a beam in a top hat profile, that's clear. If you would have a femtosecond laser or a picosecond laser, you would be maybe fine because you do ablation and then you ablate directly with your top hat spot and you have an ablation crater that is rectangular. This is fine. But if you have a longer pulse duration, for example, and you have a heat flow in your material, heat conduction, you can see here on the right side, that suddenly out of your quadratic shape, a round shape will appear. So that means you programmed a quadratic shape, but your process does something else with it because, of course, in your process, there's physics present, and these physics change the energy input that you just gave. To say it a bit more direct, we have the same here. And if we now, let's say we are a point on the surface of our workpiece in the middle of the spot, then we see a rise in temperature, and then the laser switched off, so then the temperature falls down again. So this means that even switching on and off a laser is already some kind of dynamic energy input for a volume element on our workpiece. And this is some kind of, let's say, temporal beam shaping. If you have a Gaussian beam and you move this Gaussian beam, for example, by galvanometric mirrors over a volume element on the workpiece from the left side to the right side, then again, it sees the rise in temperature and the fall in temperature. So again, this is not constant, not static. So there's also some dynamics in there in the energy input on that volume element. And if you have a shaped beam like a donut beam and you move it over the same workpiece or the same spot in the workpiece, it sees a different energy input resulting in a different temperature distribution on the surface. So this means that spatial beam shaping, when we do this, we already also result in a dynamic energy input on the workpiece. But now let's go to a bit more complex processes. So this is a simulation done by Andreas Otto many years ago when we were working together here in Erlangen. It's about penetration welding or keyhole welding, and you can see that there's a lot of physics going on. So we have a keyhole that is formed by the vapor pressure, and the vaporization is done by the incident laser energy. We have a keyhole, we have molten material, and we have there in the back an area where we have resolidification. So this is no longer like we project a quadratic shape and somehow our process will end up and will copy this quadratic shape to a result. No, and if you look how this looks in practice, you can see, and this is something we did at DESY, some synchrotron imaging with willingly too high a laser power, I have to admit, just to see what all can happen. And you can see the keyhole here. You can see the liquid solid front that you have here. A lot of things are happening. And then finally, and this is an image from another joint, but it doesn't matter. Finally, we have a result because we wanted to weld. So we have a weld seam and maybe we have cracks there, maybe we have pores. And so the relationship between starting there and bringing in energy with a laser beam and resulting here having a good weld seam is much more complex than the example I gave with the ablation, where you just ablate the material very quick on the spot according to the shape that you had. So we have to take into account the physics of the process much more in depth than with some other processes. Also, this results underlines this. We just did a temporal beam shaping with different frequencies in time that you can see here. And then we measured the roughness of the weld seam of the piece of metal that we melted. So we had the height profiles and we measured the amplitude, and out of the distance of the amplitudes and knowing what feed speed we had, we can calculate back which frequency this equals. And interestingly, if we have the spatial frequency counted out of that, we find in the roughness values back the frequency values that we had in the temporal shaping of the amplitude of the beam, namely the 100 Hertz, the 250, and so on. What's the take-home message from this picture here? It is that obviously we can influence by our spatial-temporal energy input what's happening in the process. In this case, we influence the melt. And additionally, it seems that influencing the melt works best with 250 Hertz. Maybe because this is something that is near a resonance frequency of the molten pool, which has to do, of course, with the material, viscosity, size, geometry, and so on. But this is another example that we are able to influence the process when it's run. Let me give you a remark here on that point. Very often we speak about static beam shaping, dynamic beam shaping. Let's say as a process researcher, I wondered a bit about that. Why? Because this is a systems technological point of view. You have your system with laser, optics, and workpiece, and then you might think, okay, my optics just include a scanner, but I don't manipulate my intensity distribution of my laser beam, so I might have static beam shaping just moving around the beam. But I've shown you a few slides earlier already that this is not true, because what we should have to look at is a volume element on the workpiece and what this experiences, if this experiences some static thing or some dynamic thing. So we should like to rather look at the dynamic energy input, which resembles a process technological point of view. So let's call it the spatial temporal energy input that we want to look at. And this is important. And what I've shown also in the examples before is the time scales of our process seem to matter a lot. I stick with this welding example, with the keyhole welding. You know, we have time scales that we can maybe control the vaporization. The vaporization defines the keyhole, by the way, and the keyhole then and its temperature distribution are, together with other things, responsible for the molten flow, for the melt flow around it. So this is the next thing to look at, which the fluid dynamics, which have a bit slower dynamics. The next thing you could look at is the solidification front in the back, which is of course influenced also by these. And in the end, the microstructure that will result out of it, which also depends on the things that happened before, also the energy input, so they are also connected, but of course a bit more indirect, because the energy input was there, vaporizing everything, and then there's the whole process dynamics in between and how they are coupled, but in the end, we have the solidification. So all of these, in principle, can be influenced to different degrees, of course, and we should see if not we can use this maybe. And one thing we did was we wanted to abstract all this a bit and had at first the idea, okay, as more changes of as more phase transitions we have, as more complex our process will be. So this might be somehow true for the first ones here, deep conduction welding, deep penetration welding, additive. But then we have this USP process, the ablation process, that has 3-phase transitions, so it should be the most complicated. Interestingly, it was not, because if you program a quadratic shape, you might ablate a quadratic shape. So it seems to be easier than, for example, the keyhole welding. So the question should rather be which process dynamics are relevant for, on the one side, in-process defects like spatter, or post-process results like if you have cracks or if the hardness is not as you desired or the microstructure varies that you don't want to have maybe. So then the question out of that arises, what is then the correct feature, or let's call it sub-process like vaporization, wet movement, that we should address to control these process defects and post-process results that we want to look on. And last time I stick with a keyhole welding just to show you that the time scales are differing. So if we look for the vaporization, we are in the hundreds of microseconds regime. If we go to the hydrodynamics, we are in the milliseconds regime. And solidification, we are larger than tens of milliseconds. So they have their different regimes. And in principle, you can address them by a spatial temporal energy input directly, but knowing that all of them are still coupled. So that means if you change one, you might partially change the other one because they are coupled. And this makes the whole thing a bit more complicated than it would be cool. This means each feature or its sub-process has its own interaction time, and we want to be able to address each time scale of each feature to allow the best possible control of the process. So we have to come with our spatial temporal energy input to some kind of a feature synchronous energy input. Remember the slide I showed the 250 Hertz? That was obviously somehow feature synchronous because we had the best transfer of our frequency that we did as an input into the roughness of our weld seam. But now I said dynamic beam shaping and DED. So some of you might think, okay, when I'm doing DED, well, you know, I have many layers and I have heat involved and everything, so I don't have a keyhole, or at least I don't want to have one in most of the times. So how should that go together? And I want to give you a few examples that we just started to test and where we did some experiments on. First, of course, we used this system with the Civan laser and a machine that was built for us by Lenovo. We have a free beam optics in there. We can change the focusing lenses. We have 4 powder feed lines with a separate flow sensory to be able to mix our powder online in the machine. And we have some process monitoring and process control features as well in 1D and in 2D measurement devices. To go to high throughput investigations, the machine is also equipped, but I'm not using this in this presentation, with a robot that can automatically transfer the samples from out of the building area into LIBS, for example, to see what is the chemical composition and put it back. So this is for fast testing of different alloys. This is a look into the processing area, and you can see the dotted red line is the laser beam that goes there. We have a laser for illumination because we use high-speed cameras. We have, of course, a powder nozzle shown here in yellow. And in blue is the high-speed camera with the lens system. And we have a two-color pyrometer that is standard as a standard mounted here. We can anyway mount other devices if we would like to. So this is the process, DED, directed energy deposition, as you most probably know it, with the shielding gas, and here you can already see powder flowing in that small high-speed video, and the molten material building up. Of course, when you use laser cladding, then you have less layers. It's roughly the same process. The boundary conditions change, of course, if you build more and more layers on top of each other. So what can happen if you have such a process? And I pointed out a few things here with some images not showing all of the defects that can happen. So if we do not have the appropriate local input of the thermal energy that we would like to have, we can have spatter, we can have low powder efficiency, we can have gas porosity, as you can see here. We even can have hot cracking in the parts. If we have not enough energy, maybe because we start our process and everything's cold, we might have a lack of fusion. That all can happen, and this is more the local thing. But we also have, of course, global things we have to look at, global possible defects or global effects that can lead to defects. If we have too much energy in there, too much heat, we can have layer melting in there that leads to geometrical inaccuracy. We can have an unwanted microstructure. I'm going to talk about that a bit later. This might be coupled to also unwanted hardness changes, and we might even end with some delamination or cold cracking of our part that you can see here. There's, by the way, multiple reasons for it. If you have your base plate out of another material, then you build up. So this can easily happen. If you have the same materials, maybe it should not so easily happen. So before I go to the examples, one more trying to, let's say, categorize a bit the things. We have a melt pool level where spatter can happen, where powder efficiency matters, where we can bring in gas porosity. We have, let's say, the cool down level directly after the laser beam where hot cracking can occur, but we already lay the boundaries for the microstructure. At the layer level, a lack of fusion can happen. We again, microstructure buildup we have here. And at the part level, so if you have really several layers or a lot of layers, we have to see if layer melting, geometric inaccuracies, unwanted microstructure, hardness changes, and delamination might happen. So what we can see here from melt pool level to part level, of course, the process dynamics in the melt pool level are quick, as I've shown roughly in the example with the welding. Whereas if we go to part level, dynamics are slower and slower. But we also have, and especially in DED, when we build up a lot of layers, we have an influence of residual heat that is lower if we are at the melt pool level. So we still see it because if we don't have room temperature, but a higher temperature where we start melting. So we should already realize it. But looking at the microstructure, if we go to part level, the influence of residual heat is really a big influence. And I'm going to comment on these a bit in the next slides, which will show, and I think this slide already shows it, that it might make sense if you want to influence these things that are shown here, that might make sense to use different beam shapes to counteract certain defects that might be able to happen. So if we have single weld tracks, can we see, so does dynamic beam shaping have any influence? I think this is the first question that anyway we have to ask. Why? Because we have blown powder in the process, and we all know if you have particles in a beam, in a light beam, these particles act as scatterers, and maybe you can program a beam shape, but there will be nothing left of this beam shape when the beam hits the surface. So this is not the case. You can see in this video, we switch now from the Civan logo to the logo of my institute. And you directly, you can again, so it's repeated all the times. So it's making a bigger melt pool, of course. And there's already powder on the way. You can see this, so powder flowing around. So the direct answer, quick answer is yes, there is an influence. So even though there's powder, we see an influence of beam shaping by, let's say, manipulating, controlling the melt pool shape, which maybe is expectable. So we did some experiments on that. We programmed several shapes. Some of them, or most of them, you can see here, like a circle, a quadratic shape. You have seen that, and two triangles in opposite direction towards the feed speed. We did some high-speed imaging. We did a thermal process analysis that is still a bit underway. And of course, ex situ characterization to see what's going on. And here we compare, of course, Gaussian mode with the donut mode. You see the powder flowing, and with 500 watt, you can see here very high frequency of our high-speed camera. And of course, you see that the donut mode is directly imprinted in our material. So the powder flowing around in this case has no, or at least not a visible influence on our beam shape. So this is still possible, which is a good news, because this means you can still influence your process on the melt pool level. What we then did is we changed, so we did a sequence from the Gaussian mode to the rectangular shape, triangle, donut, triangle, other way around. And we automatically, so we did high-speed camera images as you've seen them just right now, and we automatically captured the melt pool geometry and calculated out of that in pixel the melt pool area. And as you can see, and as you would maybe expect for the Gaussian mode, the melt pool area seen from above is lowest. The highest melt pool areas are for the quadratic shape, and also for the donut mode, but this is not so pronounced anymore compared to the triangles. But again, you have to take into account that these side maxima we have also influence and heat up the material. So we do not have only these green intensity distributions, we have also the other intensities in there, so that it's not 100% that. The interesting thing is when you switch between these, you see effects like here. It takes a bit of time, sometimes even a quite long time, until the melt pool area stabilizes with the new intensity distribution. Again, you see it here, and it seems most pronounced when you go from a larger melt pool area to a less large melt pool area, or saying in other words, when you go to a large but very flat melt pool to a not so large but deeper melt pool. This takes a longer time to adapt as the other way around, which is quite interesting because you might want to use this when you switch. You might want to switch your beam shapes when you try to form certain geometries and are maybe at the boundary of a part or are in the inner area of a part. So it's interesting to know this and to see that you create dynamics that are slower than your switching speed. We also did some temperature measurement. We have to be a bit careful with the interpretation. Why? Because you see that here one of the lowest values is for the Gaussian mode, which is definitely not true. But the ones of you that already used pyrometers for temperature measurement know that you have a certain area for your measurement, and you have an averaging over the area. And if your area is bigger than your molten pool, which happens for the Gaussian to be true, then you get an average between the molten area and the surrounding still solid area, which is the explanation why this is not correct. So the temperatures here in the molten pool area are higher than with the other ones. But you can see also this is measurable, and you can use this as an input if you want to control your temperature. If you want to, for example, if you build up several layers and you have already some heat in your material, some residual heat, then you might use this for controlling your laser power and also your beam shape to balance the results of your actual layer. This can be also seen in the infrared camera images. So you find back the geometries more or less, and also out of them we could calculate average temperatures. So this is nice, but this is not yet something you might say, oh, okay, it's a good idea if I can use the temperature for changing my beam shape and changing with this the area-wise energy input to avoid a melting that I don't want. But as well, as mentioned, we have different weld pool depths that we create, especially for the larger ones, this one and the quadratic shape. They create shallower molten pools, whereas the other ones create deeper weld pools. And as you probably might expect, this results in different microstructures. So here, of course, we have the deepest molten pool, and we reach a cellular solidification morphology, the same for the two triangles, but for the quadratic shape as well as for the donut shape, we have a more columnar solidification morphology. So that means a change in our beam shape resulting then as a next step, talking about the chain of process physics, resulting in a next step in a shallower melt pool results in higher cooling rates, and these results in change in microstructure. So this means, again, you can use your beam shape not only to control your melt pool, but also to control your morphology, your microstructure. As well, and this shows the penetration depth, if you, out of some reasons, want to have different penetration depth in different areas of your part, of course, this comes as well with changing the beam shape. And also coupled to this, if you remember again the process chain, we have a different microstructure, also different microstructure, depending on the material that you use, results in different hardness values. And again, here we have, as we expected, for the fastest cooling situations with the bigger molten pools that are shallower, we have the highest hardness. So also the hardness can be locally tuned by changing of the beam shape. So this is a summary. So I'm not going a lot into detail because I think it was not so many slides. I just showed you that you can control, of course, the molten pool. With the molten pool, you control as well the temperature distribution, the depth of the molten pool, and by that, the cooling rates, and by them, the micro hardness, as well as the microstructure. So, and this can be changed with different beam shapes. Yeah, then next question is, okay, we've we can do this, but then we had the idea, okay, is this really always the case? So does the powder in a DED process really never influence our spatial temporal intensity distribution or energy input? And here the short answer is it does influence. As you can see here, we had the same power, the same feed speed, but we went up with a mass per time from 4.7 gram per minute over 6.5 to 9.8 gram per minute, which is, and you can see it in the high-speed video, it's really a lot, and it's just shown here for one, again, programmed beam shape, which is 9 dots in a quadratic shape. And then we tested what would be the outcome of these different powder flow rates and beam shaping for the process. And again, we changed different beam profiles that we had. This is a slightly different set than I've shown you before. And whereas with the flow rate of 4.7 gram per minute, we still can see a different microstructure. So that means we still can influence the process via beam shaping. If we have the 9.8 gram per minute, it was no longer possible to detect different microstructures then. So that means let's say the diffraction, refraction, absorption of the powder particles in the beam redistributes, attenuates and redistributes the light beam, and by that, let's say, erases the shape or at least changes the shape so that your shape, in a certain way, your shape might not arrive anymore. Of course, I have to say that this is a bit of an unfair thing for the beam shaping. Why? Because we drove the process to the max, so we did not change the power and not the feed speed. So we just want to have a maximum of powder particles in the beam to see what happens. And we can come here to we've seen here some limitations, which in the end is not a final answer, by the way, because you can look through raindrops and have super resolution. So why shouldn't it be possible to have scatterers in your beam and know about a statistical distribution of the scatterers and use them again to get your beam shape that you want to? But this is a bit of future outlook, what I'm mentioning here. Next thing, let's go to multilayer. Now it's getting even more interesting. What's about the created microstructure? So what we did, we used a super duplex stainless steel consisting of austenite and ferrite. And you can see here, austenite is shown in blue and ferrite is shown in red. And usually when you process this in powder bed fusion, you have a lot of ferrite, but you lack a bit of austenite. And you want to be able to tune the mechanical properties of your part, to tune this content locally. Nevertheless, you should be around the 50-50 and be able to tune it there up and down, but not having, let's say, 80% of one and only 20% of the other one. We tested here two beam shapes. Let's call the one is the star-like shape and the other one is the diamond-like shape. The upper one is diamond, the lower one is star-like. Here you do not see too many differences. We did then metallographic preparation and EBSD and viscous hardness tests to see what was going on. So high-speed imaging first. On the right side, you see the star-like shape, which results in a smaller but deeper molten pool, as you can also see here with the cross-section, where here we have a diamond-like structure, which results in a wider but shallower melt pool, as you can see here. Again, the things with the penetration depths that I already mentioned apply as well here. Looking a bit more to the microstructure, you can see with the star shaped here on the left side that especially in the lower area, so the base plate is directly here, it looks quite interesting because it looks like the grains depart a bit, so they have a divergence angle. But that means that for the higher areas of the build, just one direction, let's say, maximizes out, which is this one that just goes straight to the top, whereas the other directions here are cancelled out because they have a divergence angle and go to the sides. This does not happen so much with the diamond-like heat input that we can see here. So there is already differences that we can see in the morphology here. If you look at the crystallographic orientations in the build direction, as you can see here, and we have the BCC, which is the ferrite, and the FCC, which is the austenite that you can see here on top. You can see very pronounced growing directions for the star-like. This is what I just mentioned. The other ones have cancelled out on top. So we have really those directions very, very pronounced, which is not as much the case for the diamond-like structure as well. Also for the FCCs, we see they are more widespread in the directions, but also here they are, let's say, still a bit more condensed for the star-like structure compared to the diamond-like structure. So interestingly, what we see when we look at the top of the part that we built, we have a lot of ferrite, as you can see here, for both of them. A bit less for the diamond compared to the star, and accordingly the austenite behaves differently, which is interesting. And at the bottom, and this is of course the influence of the residual heat that we get when we build up our part, we get much more austenite than we had originally on top, and our ferrite is quite reduced, and we are in an area already where you can see we still have an influence of our beam shape on the content, even in the area that was influenced by residual heat. This is, by the way, no wonder, because you might also experience, if you build a part, let's say, by powder bed fusion out of a certain material, and you want to heat treat the part, and you do the heat treatment via the heat treatment book that is 50 years old. So let's say the standard heat treatment, the resulting microstructure might not be the desired one because your starting structure was a different one. So of course, after heat treatment, and let's call this an internal heat treatment that we have here, this changes the microstructure. But the starting microstructure has a big influence on the resulting microstructure. So this again brings, let's say, the causalities from the microstructure back to the beam shape. And this also is represented in the hardness values, as you can see here. So for the diamond-like, we have higher hardness than we defined in the star-like shape. So the summary, I think I don't need to go into detail again, because I just mentioned the causality in the process, that via the beam shape you even can go into the lower layers, even though they have the influence of the internal heat treatment. We did some other very interesting, let's say, tests. I mentioned that we have the 4 powder hoppers that we can use, and it's one of the advantages of using DED, that you can, during printing, create your own material. So we tried, is there maybe something that has an influence? So can beam shaping be useful there? Yes, no, maybe. Let's see. We tried memory shape alloy, so titanium nickel that you can see here. So we wanted to be in this area here, that is the red area, by using elemental powders and mixing them. And you can see here things happen, and this is just, I'm just reporting here some first experiments. This is by far not the end. We just started with this. We found eliminations, partially they are also, we can attribute them already to of course, CTE mismatch between our building plate and the part that we built, and remaining stresses. So this is again what we did. We did again high-speed imaging to see what's going on, and again metallographic preparation to see what we got. These are the beam shapes that we tested here, and you see, I think, all the 6 high-speed videos from above, which, why did we do this? We wanted to see if we can see some flow movement. Because when we say we want to mix materials, it might make sense that we have processes that somehow create a flow, a molten material flow, or a better molten material flow than others. And these might be then more suitable for mixing the elements in the melt pool than others. So that is the idea behind. And we'll just check it. So this is what's the outcome in cross sections, and depending on your screen, you can see it or not. We already raised the contrast of the images a bit, but you can see like some do not exhibit a very good mixing of the nickel and the titanium. Here, some others exhibit some voids, some defects. Again, here not very good mixing. Whereas these here, they show a very nice mixing actually. So the 2 lines, as well as this line setup shows quite nice mixing. So what we did, we chose 2 out of them. We chose this line profile or beam shape, and we chose this flower profile. And so we have dual lines here. They really do a good mixing, but we had the idea it might be a bit, as you can see here, crack susceptible more than maybe others. Why the good mixing? This is just due to the temperature difference that we bring in. So let's say we intentionally create a higher or a stronger Marangoni flow as we maybe would need to do, but this leads to the good intermixing of titanium and nickel. With the flower with the 4 peaks, they have less dynamics, and you can see this also here in the 1 layer that we built here, or 1 line that we built here. It's not so well mixed. It's not so susceptible to cracks. That's an advantage, obviously. So we built a bit more layers. This looks funny. Please let me explain, because at first sight you might say, oh, both are not working. Let's start with the upper one. This is the one that does the good mixing, and you can see the good mixing in the lower layers. Very good. We did not do temperature control during our process, which we should have done maybe. So that means we got some overheating when coming to the higher layers, and then the mixing was not so good anymore. Why? Because the Marangoni flow was not so pronounced anymore. And in the end, and this happened during cooling down, we have a crack. Between our part and the base plate, they have different CTEs, by the way. So differing ones, that could be a reason. The one that has not such a good mixing but had less cracks, so the flower shape, exhibits in the lower layers what we predicted, not so good mixing. In the upper layers, interestingly, it has a good mixing. And in this case, it's different, because if you look at the crack and look at the shape that you find here, you can conclude that the crack already happened during the buildup. Otherwise, we would not have had the material flowing down here. So this means we had interrupted heat flow in our base plate, making our part even hotter here. And then suddenly, interestingly, we had enough mixing or intermixing of our elements. So this is, let's say, the status where we are at the moment with the nickel titanium memory shape alloy, which we did a few years ago already on a powder bed machine. It's quite, let's say, I think it's a quite interesting result. I'm not going into detail here. Hot cracking risk susceptibility, not to be too late. I'm going a bit quicker here. We chose a complex nickel-based superalloy to see if this is hot cracking susceptible. We introduced a beam shape. We thought this might be much cooler than a ring shape, this one. You might know where this comes from. The shape of the molten pool plays a big role, bringing in micro cracks, hot cracking already that in a DED part might lead to larger cracks and even come together and crack through the whole part. So we compared this, and this is the pictogram that shows how the intensity distribution was over. So to the right side is the feed speed with a ring shape, or in this case with a conventional defocus. And you can see here we have more pronounced cracks that we do not have, or do have less in this one here, in this region. We still have some, so it's not, it doesn't go to zero, which would have been fine, but we have small delamination effects here as well as in these, where they appear to be different in when they happened, but not going too much into detail here. And this image we have only from that here. So again, we have a columnar structure. We have a low misorientation, so the grains go away from each other. So that should prevent that if we have smaller cracks, if at all we have the smaller cracks, that they sum up and form a bigger crack, which is obviously in our 1 or 2 examples that we did with this, not the case for the ring shape, where we have a boundary, a grain boundary going from top to bottom, which is, let's say, an easy thing for crack going through there. I'm going to make this even shorter because now we go from the experiments to some question you might have, like, okay, there's an infinite number of beam shapes, especially if you talk about spatial temporal beam shaping. How can I start? We did something, we just did some simulations and some very straightforward things. We just created a low fidelity model, only taking into account temperature and a certain number of points, and then randomly create temperature distributions by random beam shapes. And then we did this for, as you've seen, 200,000 of these, because the computations time was very low. And then we said, okay, which one has the lowest melt pool temperature? Which one has the lowest thermal gradient? And out of that, we could filter out of the 200,000 the ones that obeyed these boundary conditions best. And we did not test always, let's say, first position for this boundary condition, but also the second one. And as you can see here, if we switch between the two, they are quite similar. So that means that the boundary condition as a selection criteria for the results of the 200,000 random creations works quite well. But this was really low fidelity. We compared it with colleagues from University of Twente with a high fidelity simulation to see if at all something like this is feasible with a high fidelity CFD simulation. And then we compared the ones one against each other. And we found that, well, as you can see here, just compare the black and the red dots. For some areas, it's comparable, for others not. Why? Because our low fidelity model doesn't include evaporation and everything. So that's it doesn't include convection, which the high fidelity model, of course, does. But as a first hint, for which beam shape you want to go, if you can define your certain boundary conditions, this might be a way to start. As long as we do not have the high, and this one went even better for maximizing thermal gradient. As long as we do not have the ability, let's say, to use our high fidelity simulations and let them optimize backwards. So the take home message is from this webinar, in my opinion, is I think limitations in beam shaping in the systems technology level are, for me as a user at least, more or less solved. we have to keep in mind that the beam shape does not equal the process result, but the beam and the movement, they define the spatial temporal intensity distribution on the workpiece. And if we are able to adapt this, we adapt the energy input, we control the process dynamics, and with this, the process result. So it's a causality, like a chain of causalities that goes there. And I've shown you several examples that show that on several time scales, it's possible to use beam shaping in DED and get good results. If we would be able to use this in a closed loop control, this would be even better, not only for DED, but for the whole laser processing community, because I believe then we could be able to really process defect-free and have even processes that are not able up to now. With this, I want to conclude with an image from a very old film that is maybe not fitting best to the time, but at least there's a laser in. This is from 1964, from James Bond. And I like this scene. Why? Because there's, let's say, Dr. No asks James Bond, do you know what this is, Mr. Bond? And Mr. Bond says, no, it's not rocket science, is it? Yeah, this is, I think, we have to think about this. Is it rocket science or not? The way we are treating at the moment the questions of spatial temporal beam shaping in laser processing is really getting deep into science. With this, I would like to end my presentation, and I'm happy to answer questions. Thank you.
Thank you very much, Professor Schmidt, for the fascinating talk. We have a few questions. I will start with the first one is, do you have any experience with applying the beam shaping for DED with wire? And then the follow-up question for that, if you do have, do you think that beam shaping can improve the resolution of the surface roughness printed part to use for DED wire?
Okay, I have no experience in using wire DED yet, but I have experience, or we have experience in using wire for alloying. So this is very near for surface near alloying. And yes, as we can influence with a beam shape very quickly the amount of energy that hits our wire for preheating, for melting, and as well our part for heating and melting, we can create our melt pool, and we can even create an intermixture, a better intermixture. So yes, I did this already a few years ago. In this case, we were not so far like now with brazing. You might be aware of the process laser brazing for connecting parts, where you also have a wire, and normally you do this also with hot wire, and you also need to balance the temperature control. So in my opinion, is that this has benefit. Yes.
Thank you. We were asked if the webinar is recorded and could be sent. So the answer is yes. The webinar will be sent to the participants who registered. And one more question, if you don't mind, I will take this one. The question is, has DBL been tried in laser metal cutting of thick sheet metal to see if this improves surface finish and quality of the cut? And I can say that we do know of users who have used the dynamic beam laser for cutting. In general, it's there's not a strong business case to use this very high-end laser for cutting with the existing solutions out in the market, but from the trials that were done, it has definitely been able to see the influence on the roughness of the cut with different beam shapes. And with that, just on time, with a little less than a minute left, I would like to thank you again for the webinar and all the participants. And if there are any questions, you can send them to the email as you see here, or to me, and I'll be happy to make sure that you get an answer. So thank you everyone for participants, and wishing you all a great rest of the day or evening, depending on where you are.
Thank you.